Another great invention triggered a revolution in communications. This tiny transistor made it possible to create portable radios, personal stereos, MP3 players, computers, and even space travel. In the 1940s, television sets were as bulky as washing machines. Radios were too big to carry, and computers filled entire rooms. That is because they all ran on vacuum tubes. Vacuum tubes work by controlling the movement of electrons in a space that is empty of matter, or a vacuum. Their ability to control electrons makes them useful as switches. When a vacuum tube receives a control signal, it generates an electric current. When the signal stops, so does the current. But vacuum tubes were unreliable because they often burned out. They also consumed large quantities of power and generated a lot of heat. Vacuum tubes were large and could not be miniaturized. At the end of World War II, a team of researchers, William Shockley, John Bardeen, and Walter Brattain, began developing a semiconductor switch, or a transistor, to replace vacuum tube technology. A semiconductor is a substance that conducts electric current better than an insulator like rubber, but not as well as a conductor like copper. The first semiconductors were made from the element germanium. Today, most transistors have silicon semiconductors. When they are cooled, semiconductors act like insulators and do not conduct current. When they are mixed with some impurities, they conduct more current. Because they can be made to conduct current or not, they can be used as switches in computers and as amplifiers in sound equipment. After repeated trial and error, Shockley, Bardeen, and Brattain found success in 1947. They amplified an electric current when it came into contact with a germanium crystal semiconductor. This amplification became known as the transistor effect. And in 1956, the team received a Nobel Prize in physics for their discovery. Transistors quickly became the key component of almost all electronic devices, including radios, telephones, and computers. Produced as individual components, transistors were connected to other electronic components to make up transistor circuits, which were smaller, faster, and more complex than vacuum tube circuits. But transistor circuits had their limitations. Individual components were made separately and connected one at a time. Making the circuits became a laborious and expensive process with unreliable results. In 1958, the engineer Jack Kilby, who specialized in electronic circuits, tackled the problem when he began working at Texas Instruments.
The answer was to make all of the components that were required in a single semiconductor.
Kilby proposed that the entire electrical circuit, including transistors, could be made out of the semiconductor material itself. Kilby received a patent for miniaturized electronic circuits in 1959. At the same time, Robert Noyce developed a similar device called the unitary circuit for the Fairchild Semiconductor Corporation in California. Noyce went on to co-found Intel, the company best known for the microprocessor, a device found in most modern computers. Today, Noyce and Kilby are considered co-inventors of what has become known as the integrated circuit. Kilby and his colleagues at Texas Instruments put the power of the integrated circuit to use in 1967 when they invented the first handheld electronic calculator. Kilby and Noyce laid the groundwork for modern microchip technology when they proved that large, complex electronic components could be miniaturized on semiconductors. The microchip, a small piece of silicon that holds a large number of integrated circuits, has made countless innovations possible. Almost every modern device using electricity contains a microchip. In a span of 60 years, engineers have made extraordinary advances in electronics. Yet little has changed in the fundamental design of microchips over the past 30 years or so. Today, single microchips hold millions of transistors, and they all fit on the tip of a finger.